Have you ever wondered how the grocery stores you shop in are continuously stocked with fresh produce each and every day? Have you ever wondered how exterminators keep unwanted pests from entering your home? The way that both of these things happen are through the use of very important substances known as pesticides. Pesticides are very important for controlling various pests and disease carriers such as mosquitoes, ticks, rats, and mice. These pest and disease carriers can be harmful to humans, wildlife, and the environment, so pesticides are extremely important methods of counteracting the effects of these things. Pesticides are also used in agriculture to prevent weeds, diseases, and insect infestation. Pesticides allow more food to be produced on a given area of land by protecting crops from weeds, insect pests, and fungal diseases, which increases revenue from farms. Pesticides are chemicals, and like other chemicals, they have certain properties that govern their effectiveness and fate in any given system. They vaporize, oxidize, hydrolyze, and metabolize. The differences in properties and reaction rates are what make them useful as pesticides under given conditions and influence their importance as contaminants of the environment. There are many, many different types of pesticides, each of which targets or is effective to specific pests. For example, insecticides are used to control insect pests, while herbicides are used to kill or inhibit the growth of unwanted plants known as weeds. The use of pesticides in agriculture dates back to the beginning of agriculture itself. The first generation of pesticides involved the use of highly toxic compounds, such as arsenic in the 1860s for the control of pests like fungi, insects, and bacteria. The second generation involved the use of synthetic organic compounds, which has had many positive and negative effects through the years since it was first introduced in the 1930s. Three very important groups of pesticides are chlorinated hydrocarbon insecticides, like DDT, dichloro, diphenyl, trichloroethane, phosphate insecticides, like diazinon, glyphosate, malathion, and carbamate insecticides, like carbofuran, aldicarb, and carbaryl. Hydrocarbons are molecules comprised entirely of hydrogen and carbon atoms, often derived from carbon-based fossil fuels like petroleum oils and coal, while chlorinated hydrocarbon insecticides are specific hydrocarbon molecules that also have chlorine chemically bonded to them. The number of chlorine atoms bonded to a specific chlorinated hydrocarbon determines in part the properties of the molecule. The number of carbon atoms and how they are arranged in 3 dimensions also determines the chemical and physical properties of chlorinated hydrocarbons. Chlorinated hydrocarbon insecticides are virtually insoluble in water, but are highly soluble in fats and lipids. They don't dissolve in water because the polar water molecules and the nonpolar hydrocarbons don't mix. The C-C1 bond, common to all chlorinated hydrocarbons, is strong and gives high stability to these compounds. The formation of 1 chlorinated hydrocarbon insecticides, DDT, is shown. This compound is prepared by the reaction of heating chloral with chlorobenzene and sulfuric acid present. This chlorinated hydrocarbon insecticide is banned in the United States due to the harmful side effects, including the residue that is created from its synthesis that is very persistent and can end up being highly dangerous. Another important group of pesticides are phosphate insecticides, also known as organophosphorus insecticides or compounds. They are all structurally related and undergo similar reactions because all are inhibitors of the enzyme cholinesterase. Organophosphates poison insects and mammals primarily by phosphorylation of the acetylcholinesterase enzyme at nerve endings. Phosphate insecticides can phosphorylate enzymes and other parts of living systems because they have good leaving groups. One specific example of an organophosphorus compound is glyphosate, which is a compound that is used to kill weeds that compete with crops. 2 main approaches are used to synthesize glyphosate industrially. The first is to react aminodiacetic acid with phosphorus acid and hydrochloric acid. Oxidation then leads to the desired glyphosate product. This is shown here. The second involves the use of dimethylphosphate in a one-pot synthesis. Glycine and paraformaldehyde are reacted in a suitable organic solvent, typically triethylamine and methanol, to produce bis-hydroxymethylglycine. Dimethylphosphate is then introduced and worked up with hydrochloric acid, which cleaves the hydroxymethyl group from the nitrogen atom, while heating then speeds the hydrolysis of both phosphate ester linkages, This is shown here. The third important group of pesticides are carbamate insecticides. The carbamates, like the organophosphorus insecticides, are cholinesterase inhibitors at nerve synapses and neuromuscular junctions. However, the reaction is rapidly reversible and less severe. This inhibition is reversible because the inhibiting bond is much less durable. A carbamate is an organic compound derived from carbamic acid. A carbamate group, carbamate ester, and carbamic acids are functional groups that are interrelated structurally and often are interconverted chemically. The structure of a carbamate is depicted in the image. The synthesis is depicted in the image. Organic pesticides like chlorinated hydrocarbons, organophosphates, and carbamates have all been very important for agriculture in preventing weeds, diseases, and insect infestation in the crops of farmers. There are positives and negatives involved in the use of all of these organic pesticides. Overall, organic pesticides are a very important aspect of the industrial farming in the U.S. and have many reasons to still be used.